Значить, мої вступні слова будуть дуже прості. Я дуже вдячний Наташі, що вона погодилась на моє прохання. Значить, Наташа закінчила кафедру теоретичної ядерної фізики, як от Кирилін, як Сотніков, а власне, як і Пилип, і я. От, вона з легкістю знайшла можливість продовжувати навчання за кордоном, причому, на мій погляд, це один із, ну, на мій, а відповідно до всіх рейтингів. Значить, правильно я кажу, Еколь Політехнік, так?
Так.
Еколь Політехнік Федераль Лозана. Значить, ну, я міг би багато розповідати про Еколь Політехнік Федераль Лозана, але ж не про нього, чи не про неї, не про цю школу йдеться про Наташу, де вона захистила дисертацію, ну, це вона ще сама скаже. І значить, нещодавно Наташу було визнано найкращим науковцем Голландії. Значить, Голландії, ну, правда, жінку, науковця жінку, але, значить, повірте, що досягнення, які Наташа представила для того, щоб бути номінуватися на цю позицію, ці досягнення достатні були б для того, щоб вона була просто, значить, найкращим науковцем того року. От. Ну, ще раз, тепер ми переходимо в англійську і, значить, я сподіваюся, що це буде корисно і цікаво. Дякую. Прошу, Наталя.
Well, thanks. Thanks a lot. Thanks a lot for having me here today. So let me try to share my screen. Hope you can see. Can you?
Yes, it's okay.
Okay, so excellent, great. And well, it's really a big pleasure to be virtually with you, and I hope at some point I will also join you in person. I'm really looking forward to it. But for now, it's really great initiative. Let me acknowledge that I think it's really important that you keep us connected, and I'm really happy to contribute to this initiative. So today I will tell you about my work, Tunable Quantum Criticality in Rydberg arrays. But before that, let me also say a few words of my career path that I hope will be also interesting to you and also to younger generation. So my stop number one, as you all know, was indeed at the physical and technical faculty. At that time, I just learned that it's called now nuclear physics faculty and high energy faculty at Karasin State University.
It's only the department. It's only
the department. I'm sorry. But thanks for correcting. So that's a building as I remember it. And it was really a sweet 4 years that I spent there with a lot of homework and a lot of mathematical oriented homework that I think is what really distinguish our education from what I see in all other years in my research that I spent in Europe and in the US, that we're really in education in Ukraine, we really become familiarized to mathematics that we're going to use later in our career so well that it's just not an obstacle anymore. So we could really focus as a scientist on physics without thinking in terms of how we're going to do it. So that was big stop number one. And then closer to my 4th year, I realized that I probably want to move outside of Ukraine also to see how science is done abroad. And that was my stop number 2. So I'm showing you a map where I actually lived so far. So I moved from the farmost right point. You don't see my pointer, right? Yeah, you probably don't.
Yeah, we don't.
So I moved from Ukraine, I moved to this middle point in Switzerland. So really in the heart of Europe, to this wonderful place called EPFL, which is one of the 2 federal school in Switzerland. So this is really a view from campus. You see the Mont Blanc on the back. This is really amazing, breathtaking view and amazing education. It's true, it was very tough because the way we used to learn was a very different way that they used to learn. Language problem, of course. All courses were in English. Most courses were in English, but the most interesting is, of course, was in French. So my first solid-state physics course, that was actually solid-state physics 3, without ever having solid-state physics at our department, I entered and studied in French. So that was quite a challenging one. But then I really enjoyed it, and I really enjoyed doing projects with my fellows. So I completed my PhD, my master degree at EPFL, and then I decided to stay there also for PhD. And with PhD in EPFL, it's quite a special one for several reasons. First, you really get exposed to the state-of-the-art science. You are at the cutting edge of what has been done in scientific perspective, but you also get a chance to travel a lot, to see other people, to learn from other research, and also to communicate with people doing different stuff at the same department. And it's also one of the 2 in Switzerland degree grading university where you got not a doctor of philosophy, but a doctor of science. I was very proud to become doctor of sciences, and also got a distinction from the doctoral school at EPFL. And as you can see, I was just one female out of 4 people distinguished at that year. And I think that remains more or less the issue in the physics community, that there are only few females who enter the community, and even less who actually stays and continue the research. But that was my stop number 2. And then, of course, in science, we never stop, we go further. And then I moved, after graduating at the EPFL, I moved to California, and that's, as you can guess, it's the point on the far left. So I moved to the University of California, Irvine, to work with Steve White, who is inventor of DMRG. So my office was literally one of the windows, as you can see on the building on the left. And I spent there almost 2 years. The position was called Mobility Postdoc. It was also sponsored by Swiss National Science Foundation, which means they give me money to send me outside of their country to do research somewhere else, but they also give me a quite generous amount of money to travel in the world and to share my results and to learn also from other people. So during my stay in California, I also visited other places like Japan, France for several weeks, and also collaborated with people there. So that was my 3rd stop, and then I came back to Europe, actually to Amsterdam, where I did my 2nd postdoc, stayed here another 2 years, and that was also the end of my 2nd postdoc was a Corona time, so we were all locked here in Amsterdam. And here I worked also on tensor networks with Philippe Corbeau, and again you see really the building, the physics building of the University of Amsterdam, as I know it, as it was looking at the time when I was there. And then, again, Corona time, so I became a professor, but I didn't move too far. I actually still live in Amsterdam, and I commute to Delft a few days a week. So I set a group at TU Delft, and again, the long white building on the left is a physics building, and the tall building on the right is a math department building where I actually have lectures. So now I do have a group there, and I must apologize, the photo is old, but that's more or less how it looks, right? So I have a group of young, very talented students that come all over Europe. Now it's 4 PhD students, 2 master students, well, and me. And we all try to push the numerical study of quantum phase transition as far as we can. But maybe 2 years after I started my appointment at TU Delft, I also was awarded a visiting professorship at the University of Toulouse, and at the most south point that you see here. So I visit them pretty often, usually several weeks a year, to collaborate with the lab in Toulouse. It's one of the really leading lab in strongly correlated systems in Europe and in France. And again, that's a new building we're sitting in there. And okay, so this is really the places where I lived for long and worked for long. But of course, apart from that, there are always conferences, scientific visits, and just short trips for science. So I just put several drops here to share the adventure of my life with you. And of course, conferences doesn't always mean that I attend the conference as a participant or a speaker, but I also organize some conferences, and this is like the latest one that I organized at TU Delft on tensor networks for constrained system, precisely the topic I'm going to talk today. And it's really wonderful feeling when you can really, bring many people thinking and passionate about similar research interests together to create something new and beautiful. And this is also an opportunity to visit some very rare gems of our world. So this picture has been done during another conference in Peresque, and this is really an abandoned village in the lower Alps, somewhere really in the middle of nowhere in France, that has been abandoned for many years, and then it was rediscovered by some architect who rebuilt it and make out of this village a conference venue. So now the entire village belongs to scientists who come there for a conference. So it could be 1 week, there are only physicists around you, and another week there are only biologists, and another week someone else. And of course, it's also a chance for me to travel and see these places together with my family. So you see, I'm holding actually my son here at the conference, and combining family life with science sometimes can be fun, and sometimes it really looks like this at the poster sessions, but it's also manageable and also quite rewarding. So I just also wanted to give you maybe statistics. Of course, I know many of you are really physicists, but I think it's also meant as an introductory of what it is to be a scientist for bachelor students and master students. So I collected a bit of statistics of what does it actually mean to be a scientist. So in the past 2 years, I organized 2 conferences, gave 3 interviews to newspapers, like really non-scientific interviews, published 6 scientific articles. But of course, when you publish an article, someone give a review on this article, an expert view on the article, and of course, it's also our service to the community to give similar reviews to other people. So I wrote about 19 such reports last year. I attended conferences. The last year it turns out to be about 9 different countries. I give about 20 different conference talks and seminars, and of course I also teach. I teach at all levels, so bachelor and master, but also at some international PhD schools, and it also totals to something more than 20 lectures per year. I counted and was a bit shocked that I spent about 130 days away from home for traveling and conferencing and collaboration. I supervise students. It also takes a lot of time, and my rough estimate is about 300 hours. I have to earn money in the sense that, of course, I have a salary from TU Delft, but I also have to ask for grants that I could spend for my research, for some salary of my students. I do not give a number of applications I sent because it's depressing, but after all, once in a while, you do have grants and you have some money for research to pursue. And then as a computational physicist, I, of course, use a lot of computing time. And I think I'm actually the main user of Dutch national supercomputer. So it's the last row of my statistics today. So with this, I would like to actually go into physics, unless I hear some questions on this introductory part from the audience.
Yes, I do have a question.
Please go ahead.
Natalia, you have marked all locations where you have been. Is it some kind of application? Because I heard that some people are tracking their location after they have visited it, or you just did it manually?
No. I did it manually, and I just put, 1 point per country, and it's by no means a full list.
Okay.
No. And also, of course, as a tourist, I visited much more places, but I really want to show where my work led me to. More questions? No? Then exciting science. Good. So in my work, I actually, my research is actually focused at the sort of interplay of quantum many-body physics and field theory, which is traditionally also attributed a bit of to high-energy physics, although this is a bit questionable. And in my research, I study quantum phase transitions. So I really use a combination of both techniques, the numerical quantum many-body simulations and field theory that comes from a continuum high-energy limit of the theory. And the reason why these two absolutely different fields of research come together are partly based on the idea and the hypothesis of universality classes. So universality classes is the concept that tells that all phase transitions in nature are not arbitrary, but form some families of transitions that have common universal critical scaling at the critical point at the transition, or as a function of the distance to the transition. And of course, there is one example that is familiar to all of you, is a classical two-dimensional Ising transition that happens in the classical 2D model that we all have seen in classical statistical mechanics. But then one can also define a quantum analog of such Ising model in quantum 1D chain, and it turns out that all critical scaling at this transition will be identical to what we know for the classical 2D statistical mechanical models. But then one can think further about different ways of classifying this phase. And basically, every time we break a Z2 symmetry, so symmetry that leads to twofold degenerate ground state on one side, and non-symmetry broken phase, so parafermionic phase, for instance, on another side, we can expect an Ising transition, Ising universality class to occur. This is true, for instance, for strontium copper boride material that I show here in the bluish phase diagram that exhibit a quantum critical point in Ising universality class. But this is also true in water at the critical point where the first order transition separating liquid phase from a gas phase suddenly terminates and go into sort of crossover region. The very end point of this first order transition is also separating twofold degenerate thing along the first order line and a non-degenerate thing around it, and it also belongs to the Ising universality class. And in my research, I question whether such a simple symmetry argument is always sufficient, or whether sometimes we need to think broader, we need to think something beyond the degeneracy of the ground state to see the nature of the phase transition. And the story that I'm going to tell you today actually started a very long time ago, before I was born in the early 80s, with commensurate melting in absorbed monolayers. So the community has been looking at the melting of the period 3 phase, the sketch of which you see on your left, as a function of temperature. So nothing quantum here, just a pure thermal transition of the crystalline period 3 phase to something disordered at high temperature. And naive theory arguments based on the previous slides for Ising transition say that, well, we do have 3 possible location of these fat points of the atoms on the absorbed layer, and therefore there's 3 degenerate ground states that are possible to realize in this lattice. So should the transition be in the 3-state Potts universality class, and this is a really direct generalization of Ising transition where the ground state is twofold degenerate, goes into a parafermionic phase, to a case where the ground state is threefold degenerate and then goes to a parafermionic case. But it turns out that this 3-state Potts point is not realized, and the life is not that simple. And the reason why has been noticed by Hughes and Fisher, who actually analyzed the nature of domain walls. They look and see that if we try to incorporate the domain, different ground state domains into a bulk, there are 2 ways of doing it. There one domain wall that could bring particles closer to each other, and one type of domain walls that would bring particles further away. And of course, if interaction between these particles depends on the distance between them, and this is often the case in real life, right? Then the domain walls would cost different energies. So there would be a domain wall that costs more energy to create, and domain walls that would be less energetically content. And therefore, if I imagine some sequence of such ground state domains, let's say A, B, C, they could cost different energy as the sequence A, C, B. So according to Hughes and Fisher, this creates chiral perturbations precisely because of the form they wrote it in a mathematical way. And according to them, this chiral perturbation can, in principle, change the nature of quantum phase transition. So they drew the sketch of the phase diagram, saying that along one special line, when there is no chiral perturbation, this is dashed line marked with C, the transition is indeed expected to be in the Potts universality class. Again, I remind you, this is just a generalization of Ising transition to the case where there are threefold degenerate ground state on one side. But as soon as there is some chiral perturbation present in the system, Hughes and Fisher think there is a room for a new type of transition that they call chiral, until eventually chiral perturbation becomes so strong that they actually lead to emergence of some intermediate critical phase, marked here AC, and separated by some Kosterlitz-Alice and Pokrovsky-Talapov transitions. And this hypothesis has been immediately after it has been released confronted by people like Haldane, it's a Nobel Prize laureate, Bach and Bohr, who actually say that, wait a second, if we actually do a field theory for this model, then we see this intermediate critical phase has to extend all the way till the Potts point where chiral transitions are absent. So according to them, Hughes and Fisher has been correct, except there is no room at all for this new chiral transition. And then Hughes and Fisher, 1 year later, came with a counter-argument saying that Haldane, Bach, and Bohr prediction has been correct, but only at zero fugacity, or now speaking in terms of quantum system, at zero quantum fluctuations. But as soon as some quantum fluctuations are present in the system, and that's are here drawn with Z, and again, this is just a sketch, there is a room for direct chiral transition before the floating phase could open. And despite the fact that theoretically this problem remained open and unresolved, numerically, quantum Monte Carlo, the main method at that time, again, we are talking about early 80s, was unable to resolve the floating phase. The error bar was larger than the possible width of this phase. It was already a first experimental evidence of this chiral transition in germanium monolayer. And what was measured is a product, delta Q times Xi. I'll come back to this product later in my talk. And you can see a drastic difference between a 3-state Potts case of silicium, where the product goes to 0, and the chiral transition in germanium monolayers, where the product clearly pointed to something finite. According to Hughes and Fisher, this is really an indication of the new chiral transition. And because of that time, numerical simulation was really unable to resolve this transition, and theoretical justification was just stuck with these two different arguments by Hughes, Fisher on one side and Halden, Bohr on another side. Was really, the problem remained open for several decades, and it was almost forgotten until recently. It has appeared in a completely new context. Is there any questions so far about the classical systems? Okay, if not, I'm going to continue. So the classical problem was open, but then we also know that there is a classical quantum correspondence that that allowed to probe quantum phase transition precisely in quantum setup. And such a playground appeared recently with Rydberg atoms trapped in optical tweezers. So experimental setup is the following. There are a set of neutral atoms, rubidium or cesium usually, and then there is an optical laser, an optical tweezer that holds these atoms with a well-controlled distance between the atoms. And then we shine lasers on these atoms with some Rabi frequency omega, and this atom brings, the laser brings an atom from a ground state to excited state. And then there are some laser detuning and some interactions. And when two atoms are excited to Rydberg state, they interact with van der Waals potential. The van der Waals potential scales as 1 over R6 with a distance to the atoms, and this leads to a phenomenon known as Rydberg blockade, which is essentially a vanishing probability of finding two atoms excited to Rydberg state within a certain distance, Rydberg radius R. And as you can see from the Hamiltonian, the first term just describes the process of bringing an atom from a ground state to excited states. The second term is due to laser detuning, and it wants to have as many atoms as possible to be in a Rydberg state. And the last term is a repulsive interaction. Is there a question?
Yeah. Are there circular Rydberg states or not?
Sorry?
Circular Rydberg states or not?
What is circular Rydberg states? I'm not familiar with the term.
Like a circle. When the principal quantum number equals the angular momentum plus 1.
Oh, that's a good question. That's really outside of my expertise. So I don't have an answer to this.
Well, then, why there is van der Waals interaction and there are no dipole-dipole interactions and like that?
Yes, so indeed, there are levels where we can create this dipole-dipole interaction. There are levels where dipole-dipole interaction are absent or negligibly small. So I'm talking now about levels where we can neglect dipole-dipole interaction.
Probably you have circular states.
Yes, then yes.
Okay.
But as you can see, the competition between this delta, the laser detuning, and the van der Waals interaction leads to the phase diagram with lobes of integer periodicity. There are many phases with period 2, 3, 4, etc. And therefore, it really makes it an ideal quantum playground to probe this old type of quantum phase transition between crystalline period Zn order and a disordered phase. And this is just a beautiful picture to show how actually well-controlled optical tweezers are in locating the atoms. But of course, I'm going to restrict myself in this talk only to 1D case of Rydberg chains, Rydberg arrays. Now, why it is actually a big advancement for the problem of quantum phase transition? It's not only the fact that we can realize it experimentally. We already have seen the evidence in germanium monolayers of the chiral transition, but we also have a very big breakthrough in numerical techniques with which we could address quantum one-dimensional systems. And this is done by density matrix renormalization group algorithm. So before going into the algorithm details, let me briefly sketch why we cannot solve any problem that we want exactly. So as you can imagine, the Hilbert space of quantum many-body problem grows, and it grows fast. So let's assume I just have a hard boson model that would be also a model for Rydberg atoms, where every atom occupied by a boson, or let's say excited to Rydberg state, I mark as a full atom, or every site which is in a ground state or empty, I mark as an empty circle. And then, of course, the local Hilbert space of this single site would be 2. Either atom is occupied or it's empty. And then, if I have 2 sites, of course, I have more possibilities. I have 4 different states, and my local Hilbert space is 4. Well, not local, just the Hilbert space of 2 atoms. Now, of course, if I have 3, I have 8 different states, and as you can see, or as you probably already know, the Hilbert space grows fast, and it grows exponentially with the number of particles. Now, of course, due to blockade, we can say that the Hilbert space grows actually not as 2 to the n, but as a Fibonacci number, but still, this is exponential growth of the Hilbert space, and still we are limited to only small system sizes. If we want to go to system sizes of a few hundreds or even a few thousands of sites, we need to approximate the wave function. And in DMRG, this is done based on the area law. Area law tells us that the ground state of local Hamiltonians are less entangled than some random states of the Hilbert space, which means that there is some corner of the Hilbert space characterized by low entanglement where the states could be viewed as an efficient basis to describe the ground state of our local Hamiltonians. And the goal of DMRG is to write down, to try to approximate the ground state within this corner of low entanglement state without ever writing down the Hamiltonian in the full Hilbert space. Now, this can be done by first changing the representation in which we write down the wave function. Of course, you understand that the wave function can be considered as just 2 to the n different numbers of the wave function. But at the same time, you can view it as a tensor with n legs, and each leg has dimension 2, right? It's the same 2 to the n numbers, just arranged in a different geometry, in a different way. But as soon as I rewrite my wave function as an n-leg tensor, I can also use linear algebra approximation of this n-leg tensor and say that, well, I can also think about it as a collection of n tensors of smaller rank, let's say up to rank 3, and then I connect these tensors by basically passing the information that they have through additional legs. And now this auxiliary leg that just connect the different parts of my physical system into a single tensor network called auxiliary leg, and the dimension of the bond of this auxiliary leg control the accuracy of my approximation. So if I would not truncate, if I would be able to write down exactly the wave function, the size of this auxiliary leg will grow exponentially fast, as well as the total Hilbert space. But now, according to the area law, I can truncate this auxiliary leg to something finite, and it would still give me a good approximation for the ground state. And not just good, but also controlled. So controllability, the main advantage of DMRG. Now, of course, I can rewrite in terms of local tensors not only the quantum state, but also the Hamiltonian. And every time you see a vertical sticking out index, this corresponds to a physical state. So let's say a boson occupied or empty. And then again, the information, how particles interact with itself, with each other, is encoded through these auxiliary legs. Again, they used to pass the information about quantum system from one side to another. And now the question is, how do I optimize this network? So let's say I start with some original guess. It could be some random guess. And I rewrite my Hamiltonian in terms of these local tensors. They are called matrix product operators. And now the question is which procedure I should really follow such that my network, my quantum state, approach the ground state. And this is the essence of DMRG algorithm. So we start with some initial guess, and then we see this 8-leg tensor. You see, every time you see a sticking index outside, this is a leg of the tensor that is not contracted. And then we reinterpret this 8-leg tensor as a matrix of some effective Hamiltonian, and we diagonalize this matrix and get the ground state of this effective Hamiltonian. We can then do singular value decomposition. This is a procedure well known from linear algebra to create left and right normalized vectors and Schmidt values, the values of decomposing a quantum state into two subsystems. And then what we can do, we can just absorb one of the states into the left environment, and at the same time we remove another state. So in this step, we updated our quantum state by just one side, but we made it one step closer to the ground state. And then at the next step, we again treat this 8-leg tensor as effective Hamiltonian. We diagonalize this, we find the ground state, we SVD decompose this ground state, and again absorbed a left tensor into left environment, remove one more, and continue until we reach the really edge of the chain, and then we can go back and update another environment. And we continue sweeping through the chain many times until we really reach the convergence. And doing so, the quantum state encoded in this greenish and bluish tensors approach the ground state. Now, what we have at the end is really a wave function. So we have access to energy, we have access to all observable that we would like to measure. It could be local correlations or local magnetization or density. It could be distant correlations. We are really not limited. We have a wave function at our hand and we can measure anything. Now, we can use this machinery of tensor networks to probe the transitions in Rydberg atoms. Are there questions at this stage? Yeah.
So you mentioned that you have local tensors. So this is essentially the approximation for the physical legs, right? So not every, so then you restrict your possibility to simulate physical systems somehow, right?
No, no, it's not really local in a sense that since tensors are connected with these horizontal lines, that's what they make information non-local. So tensors are local only in a sense that I associate tensor with some lattice sites. But the information is by no means local. It is encoded through these auxiliary legs. And we will consider later in the talk, we'll consider critical systems where the area law tells us that Schmidt values are violated and Schmidt values decay very slowly, which means that the bond dimension is actually very large. So the information is really non-local. So tensor networks are indeed an approximation, but it is not a mean field. I hope it answers.
Yeah. So you mentioned that you require still lattice, some kind of discretization, right?
Yeah, that's for sure. Yeah.
So Yeah, I know, but maybe you could comment how you proceed with continuous systems then, if you do not.
Well, there are several ways to proceed with continuous system. I'm not going to touch them during this talk, so I'm really focusing on lattice models. But in principle, you can use slice basis DMRG, for instance, or there are also continuous MPS.
Okay, yeah, thank you.
Good. More questions? No, okay. Let me proceed. So again, we're focusing really on a lattice system, and we're going to use DMRG to study this phase transition. But in fact, it turns out that just DMRG is not sufficient, because again, we see that the accuracy that we can gain, even with this advanced technique, is not enough to resolve possible chiral transitions from a narrow floating phase. So what we're actually going to use is constrained DMRG that relies on the property of Rydberg atoms that you see here, Rydberg blockade. Again, this is because Rydberg atoms interact with itself with van der Waals potential that scales so fast with a distance as 1 over R6, so it's almost impossible to find two Rydberg atoms within a certain distance. Now, how can I profit from it? First, of course, I can see that unconstrained Hilbert space, where everything is allowed, scales faster than the constrained one. So if I completely exclude from my Hilbert space states where I have Rydberg atom next to each other, this is nearest neighbor blockade, shown here in blue, you see that the Hilbert space grows still exponentially, but slower, with smaller slope. And if I exclude states with next nearest neighbor blockade, it goes even slower. So that allows to reduce a bit the computational cost, in a sense that if we are limited by computational resources of a given bond dimension, that's what controls the accuracy and computational cost of our approximation. Of course, it is better to approximate some original Hilbert space which is smaller than unconstrained Hilbert space. But on top of it, there's also a very interesting observation that such blockade can be encoded efficiently into DMRG. And in order to introduce it, let me introduce a fusion graph. Basically, it's a rule on how I go from one state to another with Rydberg atoms. So imagine that I have a chain that ends up with a Rydberg atom in a ground state. This is empty circle. Next to it, I can put a Rydberg atom in excited to a Rydberg state. That's a filled circle, and that's the first line that you can see. So if I mark my empty circle with 0 quantum label and filled circle with 1, I just go from 0 to 1. If I have a Rydberg atom at the end of my chain, I cannot put another Rydberg atom next to it. So I cannot go from 1 to 1. So this defines me a fusion graph. And now if I try to plug this fusion graph into network, I see the top left thing. So I can have two empty sites next to each other, but for instance, I cannot have two filled sites next to each other. And therefore, my matrix, tensor network matrix, has 3 blocks filled with each other, with one fourth block at trivial zeros. Well, it's nice, but it's not the structure that we actually want in tensor networks, because what we actually wish is to have a block diagonal structure, because then all contractions, all numerical operations can be done block by block. And therefore, instead of a big bond dimension D, I can have a small bond dimension D in my complexity scaling. And the way to do it is, for instance, to place tensor network tensors not at every lattice size, but in between. And then what I did, I also span local degrees of freedom over several Rydberg atoms, well, 2 in this particular case. And as you can see, every pair of tensors would then have one boson in common. And I can use a state of this boson, because it is either occupied or empty, but for both tensors, as a thing that creates just naturally one-to-one correspondence between my auxiliary legs. So it creates a block diagonal structure artificially. And precisely because there is the local Hilbert space is not 4 but 3, I gain a bit in computational cost. So using this constraint, tensor networks, we can reach much larger system sizes and much higher accuracy to actually probe the phase diagram. And again, having in mind the original problem of Rydberg atoms with van der Waals potential, we're now going to approximate it to a blockade model with, let's say, nearest neighbor blockade and next to nearest neighbor corrections to the blockade. And of course, it's obvious that such approximation is only valid for a narrow window through the phase diagram. So the higher we climb in the interaction strengths between the actual Rydberg atoms, the stronger blockade we need to take to approximate the interactions. But this is fine, since we are interested in the nature of quantum phase transitions, and they are governed by the idea of universality classes. So as soon as we keep the symmetry relevant to the nature of the transition, we can approximate the model as much as we like. For instance, we can use blockade models to approximate Rydberg atoms. So let me now show you the results for the nearest neighbor blockade model that will probe top of the period 2 phase and tip of the period 3. According to Hughes and Fisher, the transition to this period 3 phase could be either conformal in the 3-state Potts universality class, or chiral, or floating phase, right? The one that's suggested by Halden, Bach, and Boyle. And Hughes and Fisher also developed the idea on how this 3 scenario could be distinguished from itself. So they suggest to use the product delta Q times psi, precisely the product that has already been probed in experiments. So delta Q is the distance of the incommensurate wave vector Q to its commensurate value. Here we're talking about spin 3, here we're talking about period 3 phase. So commensurate value is 2 pi over 3. So delta Q is the distance from Q that I would measure at any point to 2 pi over 3. And psi is the correlation length. So now, how do I measure both of them? I compute density-density correlation. And of course, in the gapped phase, it would scale exponentially fast with the distance. But you can see that on top of the just exponential decay, there are some waves. And these periodic waves are precisely the signature of incommensurability. So the main slope that you see gives me a correlation length. This is exponential, the main exponential decay that you see. And on top of it, removing the main slope, what I left with is a pure cosine function. This is a bottom top plot that you see. And the DMRG data after removing this main slope are shown in blue, and I fit it with just a pure cosine function, nothing interesting here. So, and you see a perfect match with a very well identified wave vector Q. Now, equipped with this technique, we measure delta Q and psi all over the phase diagram and come with 3 different critical regimes. So let's look at the middle one first. Delta Q times psi goes to 0, indicating, according to Hughes and Fisher, conformal 3-state Potts point. In fact, for this blockade model, the location of the 3-state Potts point and the very nature of this transition is known precisely because this is an integrable point. But for us, it was very important to cross-check it because it was also a benchmark for the algorithm. Now, let's look on the left, and you see a very clear divergence of delta Q times psi that would correspond to the floating phase. So what happens is the system first cross the Kosterlitz-Zaulis transition, where the correlation lengths diverge, stretch exponentially, so very, very fast, while Kosterlitz-Zaulis transition itself does not affect incommensurability, so delta Q remains finite on both sides of it. And therefore, delta Q times psi also diverge, stretch exponentially. And finally, on the most right, you see chiral transition, with the product delta Q times psi absolutely clearly going to a finite value. So doing this analysis for many different cuts through the phase diagram, we came up with the following conclusion, that there is one single point, again here it is located on integrable dotted line, where the transition is conformal in the three-state Potts universality class, again direct generalization of Ising transition to the case where there is threefold degenerate ground state on one side, and then away from this conformal point, but not too far from it, the transition is in the direct chiral Hughes-Fisher universality class until eventually the floating phase emerge on both sides of the transition. And on the scale that I show here, the width of the floating phase is smaller than the width of the red line. So it's extremely narrow. So no doubt that it was a good reason that this floating phase was not captured previously. Questions? Okay, then I'm gonna proceed. Of course, having such a zoo of different quantum criticality in the period 3 case makes us think of what would happen if I climb further on the slopes of Rydberg atoms and look at the boundary of the period 4. And in fact, if period 3 transition has been debated by great people, you know, yes, there were no consensus, but still there were some great thoughts, controversial, but still. The period 4 transition, we had very little knowledge when we actually start looking at it. And the only thing that we knew for sure that the situation is gonna be much richer, at least, because chiral perturbations are not always relevant. What does it mean? It means that even in the absence of chiral perturbations, the transition between period 4 and disordered phase are much richer. In field theory, it is controlled by so-called Ashken-Teller criticality. So you can view it as two Ising chains that are coupled to each other with some parameter lambda. And then you can think in terms of two extreme limits. Completely decoupled Ising chain, and this is called Ising cross Ising, and a system where the coupling is actually symmetric such that the local Hilbert space is 4. So again, think in terms of two-fold degenerate Ising, three-fold degenerate three-state Potts, and then four-state Potts. It's a next generalization of Ising and three-state Potts to the case where we have four-fold local Hilbert space. And what turns out is everything between these two limits of four-state Potts and double Ising are connected through a critical Ashken-Teller model that itself could be could describe the transition between fourfold degenerate ground state and non-degenerate ground state. And depending on where this conformal point is, chiral perturbation might or might not be relevant and might or might not lead to chiral transitions. So having this knowledge in mind, we start to look at the Rydberg atoms. And again, we are looking at the blockade model of Rydberg atoms, very much approximated, but the one that where we can do numerics at a very high accuracy. And this is the basic phase diagram. Again, we see top of the period 3 phase and tip of the period 4. Now I'm going to focus at the transition to the period 4 phase. And the first problem that I see is how to actually locate the conformal points. In the previous case, the location has been known exactly, precisely because it was sitting on the integrable line. Now, there is no integrable line. So the idea that I had is the following. Let's look at the incommensurate wave vector Q all over the disordered phase. Of course, close to period 3 phase, it will be 2 pi over 3, and then it will slowly decay as soon as I move away from it. But at some point, this continuous wave vector will pass through Q equal pi over 2 or 2 pi over 4. And this is precisely commensurate value with the period 4 phase. So along the special line, there should be no chiral perturbations with respect to the period 4 phase. Therefore, if conformal point exists at all, it should be at the crossing point between this commensurate line and the boundary of the phase. So for now, this is just a hypothesis that this could be a conformal point. Let's check. For this, I look at the finite size scaling of the order parameter. In this case, it's alternation in local density. And conformal field theory predicts for the Ashkin-Teller point the value 1,8. What I see numerically for the special point is 1,2,4, so it's very, very close. Also, I look at what's called conformal anomaly or central charge by looking at the finite size scaling of the entanglement entropy, so intrinsically quantum measure of the system. And again, I see almost perfect agreement with this value, which means that the point that I located this way is indeed an Ashkin-Teller conformal point. Now, the question is, which Ashkin-Teller, right? Because depending on where I am on this orange line could tell me whether there is a chiral transition or there is a floating phase or there is actually nothing. In order to identify the Ashkin-Teller point, I need to use something that is actually changing along this line. This could be, for instance, the critical exponent nu, with which the correlation length diverges up when approaching the transition. So what we see here is nu equal to 0.78, which means that it sits very, very close to this green line where chiral transition actually disappears. But it sits on the yellow side, so there is actually a hope to see chiral transition. And now we do the same trick as before. We measure delta Q and Xi over many different cuts through the transition. And we, again, measure delta Q times Xi and distinguish these three different regimes. Except now, delta Q is taken with respect to 2 power 4 and not 2 power 3. And that's what we see. At the point that we identify as the Ashkin-Teller conformal point, we see that the product, delta Q times Xi, goes to 0. Then there is a region where the product goes to a finite value, indicating this new chiral transition. And I want to stress that this is actually a different chiral transition than the one predicted by Hughes and Fisher for the period 3 case, because now the symmetry is different. It's a different universality class. And further away, there is a floating phase with a clear divergence delta Q times Xi. Now, if I try to summarize this phase diagram, it looks like this. There's one single point of conformal Ashkin-Teller transition surrounded again by the new chiral transition out of period 4 phase. And then on both sides of it, there is an emergent floating phase that eventually on the right will merge with the floating phase of the period 3 phase. But what I have shown you so far was the chiral transitions obtained in the blockade model. And what I'm going to show you now is how it appears in the Rydberg chain with van der Waals interaction. So again, using the same trick, we mark and extract the wave vector Q all over the disordered phase and keep track of the commensurate value 2 power 3 and 2 power 4 to locate the conformal pots and Ashkin-Teller points. And then we do many cuts through the transition. Again, now this is really a model with van der Waals 1/6 interactions, and we measure delta Q times Xi for these points. And what we see is again the following. So we see, and for both period 3 and period 4 case, we see that there is one point where transition is conformal with delta Q times Xi going to 0. That's what you see on your left. Then there are some cuts on the middle part where the delta Q times Xi goes to a finite value in agreement with chiral transitions. So chiral transition can also be observed in Rydberg atoms with van der Waals interaction. And then further away, and also for both period 3 and period 4, we see that delta Q times Xi actually strongly diverges. In fact, the diversion was so fast that we decided to plot it as 1 / delta Q times Xi, and that's why you see it goes to 0. So we do realize all these regimes in Rydberg. atoms. I would like now to ask whether you have some questions. Okay, if not, let me proceed.
Хорошо.
Yes?
Previous slide. Oh, yes. I see B, C, D, I see F, G, H, I don't see A and E. Why?
Oh, because that was, we compute also, there were additional plots where we compute inverse of the correlation length to cross-check that what we have for conformal points.
Oh, I see.
Maybe could you comment shortly error bars, the origin in these plots?
Yes, so the origin is the following. First, of course, we are talking about correlation length, which is not comparable, but very large to the system size. So here system size is about 300, 600, and the correlation length that we can safely extract is about 60, 30, right? So it's about 1 order of magnitude smaller, but still already at this scale, there could be some errors associated with the way how we extract the correlation length. And the main error also comes from the fact that in system with open boundary conditions, with Rydberg atoms, the laser detuning delta is not at the edges, is not balanced with the interaction, which means that the edges are sort of fixed with unbalanced interactions. And this means that our delta Q can only be defined as 2 pi over n, right? Because there is no flexibility due to edges. And this difference of delta Q define the main error in measuring delta Q times I, because really we are talking about tiny values away from incommensurability. So it's very, very close to commensurate and commensurate transition.
I see.
More questions? Okay, if not, let me proceed to a fun part. So you see here that we actually observe all 3 critical behaviors predicted originally by Hughes and Fisher and then generalized to this period 4 case. And this is very inspiring and very motivating. But now, if I take a closer look at this phase diagram, what you see is the following. So Ashken-Teller point is marked here as 80. And then you see C7 and C8 marking the cuts where we see chiral transition and the floating phase, which means that yes, the zoo of the 3 different critical regimes occur in the phase diagram of Rydberg atom, but it is just so small, the chiral transition, that noisy and maybe a bit decoherent Rydberg system will not be able to capture it. And therefore, I was thinking on either actually a way to overcome it, because of course it's not very surprising. We have seen that the conformal Ashken-Teller critical point sits very, very close to this green Lifshitz line where chiral transition actually disappears. For blockade model, we measure nu 0.78. For Ashken-Teller and van der Waals interaction model, we measure nu 0.79. So it's extremely close to the green line, and therefore it's not surprising that chiral transition is very, very short. But is there a way to actually tune the Ashken-Teller point and therefore to enlarge the chiral transition? And that was the question that I tried to address, and to understand whether in principle there is a way to tune quantum criticality in Rydberg atoms. And for this, I came to a very old idea of Igor Lesenovsky, who actually proposed to engineer new phases, and then it was not that exciting and somewhat, forgotten this idea, but the idea itself is brilliant. So the idea is to use several components of Rydberg arrays, and again, we are not talking about dipolar components. We are talking about components that interact only with van der Waals interactions. But then I can use two levels. I can shine two lasers on my system that would bring system to either one Rydberg atom level or another excited level. And I can always pick up such levels such that they are sufficiently far in the principal quantum numbers, so the interaction between blue levels are, let's say, much weaker than interaction between pinkish levels. And there's also quite a choice of levels such that blue and pink levels do not interact or interact with the interaction strengths few orders of magnitude weaker than in-species interactions. What does it mean? It means that I enlarged my Hilbert space. And again, what I'm going to show you now is a very simplified approximation of the system where I just treat the interaction as a blockade only. So I have two Rabi frequencies that brings the atom either to a blue or red level. And I have two laser detunings, again, separately for blue and red level. And this creates in total three-dimensional parameter space, exactly as I need to probe a three-dimensional phase diagram of the Chiral-Ashkin-Teller problem. And what we see is the following. So I just fix, for now, the ratio of the Rabi frequency shining on these two different components and probe the phase diagram. And what I see is I detune only strong pink component. The maximally occupied site allowed by the blockade is a period 3, and that's a period 3 phase that you see on your right. If I detune only a weak component with nearest neighbor blockade, it leads to a period 2 phase where every other side is occupied by the blue weak component. And if I detune both of them, so if I favor as many atoms as possible to be occupied, either red or blue, the system ends up in a period 4 phase where every other empty side of the period 2 phase is occupied by the strong component. So one can enter this period 4 phase either through the Ising transition into period 2 phase and another Ising transition, or as soon as the two Ising transitions come closer and merge into multi-critical point, one can enter through the multi-critical Ashkin-Teller point or through the chiral transition and then the floating phase. So now the question is whether by tuning these Rabi frequencies of the two components, I can actually affect the nature of the multi-critical Ashkin-Teller point. So this phase diagram you already have seen. This has been computed for the given ratio omega-1 over omega-2 equal 1. And for this particular ratio, the critical exponent nu, the one that controls the property of the Ashkin-Teller point, is 0.76. Now, what happens if I change this ratio? For omega-1 over omega-2, I get the critical exponent, which is much smaller. So it's 0.68. And if I change it in a different way, you see that it actually increases and nu prime is equal to 0.81. What does it mean? It means that by changing the ratio of the Rabi frequency, I can indeed travel along the Ashkin-Teller critical line. So can I actually increase the size of the chiral transition? And here is the answer. So again, for the ratio about omega-1 over omega-2 equal 1, the width of the chiral transition, let's say, is 0.25, but for the ratio which would be twice as large, the chiral transition is almost twice as large. And for omega-1 over omega-2, that's the lowest row, there is no evidence at all that chiral transition is still present. So probably it just disappears, and then the system is compatible with immediate opening of the floating phase. And of course, what I have shown you so far is just a simplified blockade model, but this is a proof of concept in the sense that by tuning the chiral Ashkin-Teller transition, we can tune the length of the chiral transition, and this can be done by simple extent of the local Hilbert space, for instance, by means of multi-component Rydberg atoms. Now, there is one more comment that I would like to add. For multi-component Rydberg atoms, there is a huge advantage over, for instance, Rydberg ladders or higher dimensional lattices, because creating several components does not mess or does not break translation symmetry explicitly by construction. So this would be, for instance, the case for multi-species Rydberg atom, where certain arrangements of cesium and rubidium atoms are predefined at the construction process before the system is driven. Here, the translation symmetry remains unbroken, and it's breaking spontaneously upon shining the lasers. And therefore, it is really an ideal to study complicated phase diagram and quantum phase transitions where more than one control parameter is needed. And this also opens a way to manipulate quantum phase transition beyond the chiral transition. It's in general the case, and one can also think in terms of dipole-dipole interactions and increasing the component there, and maybe not only manipulate but also to construct some new transitions. So what I have shown you today is the embedding or the emergence of the simplest Ising transition, but of course one can imagine that instead of Ising I can merge a chiral transition or a Potts transition or something more complicated. And that could be a way to actually engineer novel quantum phase transition directly, numerically, or even in quantum simulators. And with this, I would like to thank you for your attention and really looking forward to your questions.
Please, colleagues. Really, I personally love it myself. I'm highly impressed. But what about questions? Ilya, what is it clear?
Sorry, could you repeat the question? I really didn't get it.
О, будь ласка, Коля.
Do you hear me?
Yes?
О. Коль, ну у вас поднята рука, тому
One question.
Да.
Can please
Ну,
Wow.
Коля, you should switch your microphone. It's not switched on.
ну, я бачу підняту руку типу Бондаренка, але вимкнутий мікрофон. Андрій, будь ласка.
Поки що Коля налаштовує мікрофон. So let me ask a question. So I have a few, but maybe I start with the first one. You mentioned that for one component Rydberg arrays, the translation symmetry is broken. It's kind of I'm curious. I hear this for the first time. Could you?
No, it's not what I mean. No. I said
okay.
that the translation symmetry is broken for multi-species Rydberg arrays is when we mix cesium and rubidium atoms. So it's a
Why
single.
is it so? It's
Imagine that you have a collection of rubidium and cesium atoms, just arrange them like cesium, rubidium, cesium, rubidium, cesium, rubidium. Then you, by construction, you break translation symmetry by 2.
So you mean in tweezer arrays, right? You bring them manually, not just okay.
Yes.
Now I see. Yeah. Okay.
I mean, of course, we are speaking about lattice. So in principle, we break translation symmetry but I'm speaking about lattice symmetry, of course.
But usually in experiment, you can also make kind of averaging over random sampling of positions, right? Or this still be.
Yes, but again, if your goal is to create some original pattern of cesium rubidium atoms, then of course this pattern will be preserved in over the sampling, right? So it's like
okay.
if we're just speaking about single component, the usual Rydberg atom arrays, nothing is broken. It's still a nice translationally invariant system with some edges, probably edge effect, but I'm not considering it today.
Okay, so and perhaps you had some contacts already with experimentalists and these quantum simulator guys from Lukin's group, maybe. What do they say about this proposal?
So, well, looking at it, actually moving towards, more programmable simulators, more digital, but there is a group in Strathclyde where they want to expand their Rydberg simulators precisely to multi-components. So I'm very excited. It's going to happen probably in January 2025. I'm very much looking forward.
Who is leading professor there?
Johannes... I don't remember.
German name, right?
No. I think
No,
he's.
no.
I think he's British.
Oh, okay.
I can send it to you later.
Yeah, no.
Just
No
out
worries.
of my
Okay, great. Yeah, thank you. So they say that it's kind of realistic and not.
This is mystery for me. Yes, I mean, in principle, this is realistic. This has been done at the scale of a few atoms. It is expensive to do it on several atoms just because you need to buy 2 lasers and pay twice as much for electricity. But otherwise, it's doable. But what sounds strange to me is that they can really do any combination of omega 1, omega 2, delta 1, and delta 2. And from naive perspective, I just don't understand how anything could fit into this picture, but apparently it is. So there is, for instance, there is no strict restriction that omega 1 should be smaller than omega 2. I don't understand why, but there is no such condition.
Why should you expect it's just regulated by laser power or the tuning?
Well, yes, but if I assume that there is also a condition that the higher is the principal number, the stronger is the interaction. So it's kind of logical to assume that you need more energy to excite to a higher level than to a lower level. So to me, it sounds a bit counterintuitive if you look at the figures that I have on the left, that you can actually exchange these levels.
Thank you, Natasha. Any other questions? And once again, probably it is not my right, but I'm like a father for Natasha. I should like to emphasize that sometimes they say that физтех, it means that some crazy who do not take care of their family, and I'm really very happy that you have given these pictures with your son, which means that the life goes on, and not me, but civilization should expect your son to do something not perfectly in nuclear physics or in physics in principle, but he will do something interesting, something exciting, and so on. Then let us thank you once again.
Thank you very much.
I'm very happy with this our meeting. Thank you so much.
Thanks a lot.
Yeah.
Thank you.
Best regards.
Best regards.
We finish. Побачимось.
До побачення.
До побачення.